Really weird. We'll do it. Let's get started. So, if you go to exam prep, here on the menu, exam prep, I've started a mastery exam folder, and there are two things I've posted on this. The first is the list of rules for closed form rate of change functions. So these are the rules for individual functions that you'll have to memorize and know. I'll show you those in a second on the PowerPoint. Okay? The other is the bank of problems for the exam, actually for the second half of the exam. The first half of the exam will be real short ones like the list of rules in the previous, up there. Okay? The second half will consist of 10 problems that will come from this problems bank. Okay? They will be problems from this list. Okay? So let me just show you that quick. So the second half of your exam will be 10 of these to find the closed form rate of change function for 10 of these. You don't know which 10 you're going to get. And everyone will get a different 10. Okay? Or a different combination of 10. Okay? So you are free to, as you're able to do those. So we're gonna get into it today, and then so some are easy, some get much harder. So the hard ones we're not ready for. We'll work on those Monday. But after this week, can you stop talking, please? All right. So after today, there will be many of them you can work on this weekend if you want to get started, and then the hardest ones. Hopefully after Monday's lecture, after your recitation, then you'll be able to do those. Okay, so let me show you the list. Here's the list this is that first list I posted of individual functions that you have to have just memorized, okay? Over here on the left, these are the basic rules. You'll see that we've already done derivative of a constant, x to the n, square root of x, exponential function, e to the x. Okay, so here's two more new rules in the basic category. Natural log, this is a very common one we see a lot. The rate of change of natural log is 1 over x. And then the next column is the trig. This is one we'll do today, so I just want to highlight it. The rate of change of the sine function is the cosine function. And then there's the 5 other trig functions, and then there's the 6 inverse trig. Okay? This one actually you see a lot. Okay, so the rate of change of the arctangent or the inverse tangent is 1 over 1 plus x squared. Okay, so these are the basic rules that you have to have memorized, but then what happens is functions come in combinations of these, sums of these, differences of these, products of these, quotients of these, compositions of these, and that's where it gets more difficult in terms of finding the rate of change, because you're using all these rules in combination, where functions are made up of more than one of these functions at once. So you got to have the rules down for the individual functions if you're going to have a chance for the ugly ones, okay? So just, again, to point out, we may say today, the rate of change of natural log is 1 over x. The rate of change of sine x is cosine x. And for sure we'll see at least one of those today. Okay, so today we're going to take an ambitious course. So we're going to kind of move fast, really pay attention. We're going to work on composite functions, product functions, and quotient functions. So this is what I'm talking about, taking two individual functions and combining them somehow to make a new function. Here's 3 different ways we can do that. So let's talk about composite functions first. Okay? Composite function is a process of executing 2 functions in succession, where you take the output from the first and it's the input of the second function to get the final output. So we've done this. There's a very specific example where we've done this. Do you remember what that was? Where we took the output of one and we made it the input of the next. Anyone remember when we did that? Yeah, it was the step function. What was the step function composed of? Right. We took left x, the output of left, and we put it into the rate function, and it made the step function. So what came first? Left came first. We put x into left, and it gives us the left-hand value of that interval. And we put that into the rate function, and that gave us the step function, r of left of x. I did, thank you. I did. Okay, so here's three functions, m, p, and q, and each of those can be thought of as g of f of x. So I want you to just take 30 seconds, see if you can write down in each case, what would f be and g be such that g of f of x would equal these given functions. So see if you can do it. Okay, so you could think of, so there are multiple answers to some of these. So this is kind of, would be one way to do it. F is x cubed minus 5. Then what would g be? What would the function we'd be taking that output and putting into g to get m? Square root of x. So if you had that, then g of f of x would be the same function as m. So now that you have an example, so let's just do it. So what is f in this case? 3x to the 8th is being put into what function? Okay? So often when we look at these, we want to find the rate of change function, we ask, what's the overall big picture, or what's the structure of it? So like q, what's the overall structure, the big picture of q? What function? Sine. Is that f or g? G, right? So this one here, whatever this is the big picture of the function, or the overall structure. And so g is sine x, and then f is the function where whatever x squared, and we know that we need this in terms of using x to the n. We need to change it to x to the minus 2, which you found in your web work, right? Okay, so what about m? So if we apply the rule for m as a square root, so is the rate of change of m, is it, if we're applying that rule, is it 1 over 2 times the square root of that thing? That's kind of like the rule for square root. Or maybe we do that rule, but then we also take the rate of change of the inside? Or something else? So here's some possibilities for what the rate of change of m might be. So how can we use GC to find out? How can we use GC to find out, is one of these the rate of change of m, or maybe neither of them, it's something else? How could we use GC to find out? Okay, we could use graph. So I've got this set up here. I have put m in, and then here's that first one. I said that first possibility for rate. I'm calling it rate 1 as a possibility, and then R2 as a possibility. And I could graph those three. So here's the original rate function. Here's R1. Here's R2. So is it one of those two? How do you know? What did I graph? I graphed these two possible, or maybe possible rate functions, and I graphed what's M, the black one here. Is that a rate function? No, that's the accumulation function. So we need to compare these two possibilities to the actual rate function. Do we have that graphed?
Yeah.
No. So how can we graph the actual rate function? So if you've been paying attention the last week or two, we should have a way, you should know that there's a way we can graph and know that we're looking at the actual true rate of change function for m. What would that, how would we do that? Okay, so I heard, so some people are maybe thinking it, difference quotient. So what if we set up another function, I'll call this Rm, because this is going to be the real thing. This is our rate of change of m. Use that difference quotient, and let h be really small. And now if we graph that, so now I'm going to graph that function, and we'll compare it to the two. I'm going to turn off the original accumulation function, so we're not, because that doesn't, so accumulation function gone. Here's our two possibilities. I'm going to graph this one, and there it is. So right here is the, for very, very small h, it's the value of the rate of change function, r sub m of x. How do we do on those two guesses? Neither are right? So if one of these were correct, it would land right on top of what we know is the true trusted rate of change function. So as you're doing these examples, use graphing calculator to check your answers by graphing it against what we trust. And what we trust is our rate of change function. M of x plus h minus mx over h. So we need something else. We need something else. So let's take a look, investigate what's going on here with these composite functions. All right, so just as a review, suppose we have a function f and a rate of change r of f. And I'm going to look at the rate of change at x equals 6.1. What does the 3.8 mean? So I have an output of the rate of change function when the input is 6.1. Tell the person next to you, what's the meaning of 3.8? Go. Okay? The meaning of that is the same as the meaning as if it was a constant rate of change. So that's why we were targeting constant rate of change, because the derivative is essentially constant rate of change with one important distinction. If the change in x is really, really small, right? We zoomed in on a curve for a very small change in x. The curve looks straight, so we can apply the idea of constant rate of change. So that means if x moves a tiny bit from 6.1, the value of f of x will change approximately 3.8 times as much as however we make that little change. Okay? So delta y equals k delta x. And so what is k? K is, we can think of, k is this 3.8. So this is k, right? K is a value of rate of change. K is a value of rate of change. So for a very small change in x from 6.1, our output will change 3.8 times as much as the change in x. Okay, so we want to apply that. So here's the situation. So now we want to talk about, we're trying to figure out what's the rate of change of a composite function. So I have the rate of change of f of x equals 5 at the point 627. And the rate of change of g of x is 3 at the point 2714. Okay, what is the rate of change of g of f of x with respect to x at x equals 6? Okay, so we start with a little change of x. How much will the function f, the output of f, change if I change delta x a little bit, let's say at x equals 6. So we're at x equals 6. How much will the function f change? Will it change by 5? 5 times that, okay? So that's how much f will change. It'll change 5 times as much as our little change in x. Now, that means that we got a little change in f. And so in G, the input into G is f. So this now is the little bit of change, like a delta x, but now it's the delta f, that's for G. Okay? So if f changes this much, how much will G change? How many times as much? 3 times as much as that one. Do you see it? So G is going to change 3 times as much with respect to its input. Well, in G of f of x, its input is f. So we got that change in f, and so now G is going to change 3 times as much as that. So starting from the beginning, how much does G of f of x change when we have a little change in delta x, or a small delta x? 15 times as much. 5 times 3 times as much as delta x. And where did the 5 come from? The rate of change of f with respect to x. And where did the 3 come from? The rate of change of G with respect to f. With respect to f. Okay? So that 5 times 3 is the rate of change of f with respect to x times the rate of change of G with respect to f. Because we had that set change in f, and the change in G was 3 times as much. Okay, so that right there, that's our K. That's the rate of change of G with respect to x. And that's how we find the rate of change of a composite function. Now, when we do it, actually, we do it in reverse order. So we do this first, when we write it out, and then we do that one next. So that's what will be on the next screen. But this is where it comes from. This is where finding the rate of change of a composite function comes from. So here it is. This is called the chain rule. The chain rule is if you have f and g, having rate of change functions rf and rg, then the rate of change function for the composite is the rate of change of g. Okay. So the rate of change of the composite function g of f of x is the rate of change of g with respect to f of x times the rate of change of f with respect to x. We can also use the prime notation. Okay? It's the same with the prime notation, same thing. So this is saying the rate of change of g of f of x is the rate of change of g with respect to f times the rate of change of f. And that last screen was where this comes from. Okay, so there it is, going back to our chart. So what did we say? Let's write these out again. So this was x cubed minus 5, square root of x, 3x to the 8th, and e to the x, and sine x, and x to the minus 2. Okay, so now we know how to actually get the rate of change of, so we'll do m first. So we know it was something different than our 2 possibilities. So what does it say? It says, take the rate of change of g with respect to f. What is the rate of change of g? So we look at g. What's the rate of change of g? 1 over 2 square root of, but it's not with respect to x, it's with respect to f of x. So it's going to be square root of x cubed minus 5. But then we have time. So this is one of our guesses, right? So it was close, except we didn't have this part, right? Times the rate of change of f with respect to x, which will be the rate of change of that function, 3x squared. So after you guys practice these two, we'll go back to GC and we'll put that function in. We'll compare it to the actual rate of change. And if this is correct, then it should land right on top of the one that we know for sure is right. But in the meantime, but before that, you find these two rates of change of P and Q. Go. Okay, so what's the rate of change of g if it's e to the x? What's the rate of change of e to the x? E to the x. But we need it with respect to f. So it'll be e to the times the rate of change of f with respect to x. Okay, so now we've had enough practice in these. This is actually two rules, right? It would be 3 times the rate of change of x to the 8th. Well, these we should start being able to do in one step. It's going to be 3 times 8, which is our 24, x to the 7th. Okay? Rate of change of g, told you at the beginning of the class, cosine of x. But it's got to be with respect to f, so it's cosine of x to the minus 2, then times the rate of change of f. Negative 2, x to the minus 3. Any questions on these basic chain rule? Yes? Okay, so this says that we do the rate of change of g, first of all. What's the rate of change of e to the x? E to the x. But it's with respect to f, not with respect to x. Meaning, the input is still 3x to the 8th. You just leave, you just leave it as it is, right? So in that first overall step, you leave that inside function as it is. Other questions? All right, so now let's go back to GC and see that this is now the true exact rate of change function. So I'll make it R1. I'll change R1 to, yeah, because we almost had it, right? So this is actually what? The rate of change of g with respect to f, but now we need also times the rate of change of the interior function, 3x squared. And let's turn this one off. We know this one's wrong. And we could get fancy, and we can make h a slider. And so right now I'm showing our difference quotient rate of change with an h of 1. But if I make h small, The blue one is the one we just did by the rule. If I make h smaller and smaller and smaller, boom. So now for very small h, our trusted form, so this is our trusted form, is the same as the one we did by algebra. Okay, so we got it. Any questions? Okay, so we have not dealt with products and quotients. Products and quotients. So here's two functions, f and g. We can make two new functions. One as by making a quotient of those two. So we could take sine divided by e to the x and make a new function. We could take sine times e to the x and still make another function. So what about the rate of change? So we had that the rate of change of the sum, say f plus g. So if I made a function, let's call it w of x. Okay, that'd be sine x plus e to the x. And for a sum of functions, how do we find the rate of change? The rate of change of the sum, right? It was like falling out of bed. It's so easy, right? So what about the rate of change, say, of a product? We just do the product of the rates of change, right? And then the rate of change of the quotient. Just do a product, just do the quotient of the rates of change. Calculus students throughout the ages have tried to do that, but unfortunately, it does not work. You can't take the quotient of the rates to get the rate of change of a quotient. You can't take the product of the rates to get the rate of change of the product. That only works with sum and difference. It only works with sum and difference. So wouldn't it be nice? Wouldn't it be nice? So let's talk about product. So if we want to figure out how to find the rate of change of a product, say of f and g, what do we do? You're just making up rules? How are we going to find out? Everyone write it down. We're trying to figure out what that's going to be for a rule for rate of change. So what would you do first? We should all know this by now. What would you write down first? Everyone do it. If you're not sure, you haven't been paying attention. Okay, did you write something down? What do we know for sure the rate of change of f times g is? So we can write it down. We don't have it simplified, but we can write down what the rate of change of f times g is. How many people wrote that down? Not enough. Not enough. Okay, this is what we've been doing. This is our derivative, our quotient, our difference quotient, right? That's how we find derivatives. This is how we find rate of change. The change in y over the change in x for a change in x of h. Okay, we've done this many, many times. Okay, so what do we do with this? Okay, so here's these red terms here in the middle, these two terms right here. I've subtracted this f of x times g of x plus h and added it. So it's really, the whole thing is really just 0. So it's still equal to what's above. Okay, why did I do that? Because it works. Okay, because it will get us the result we need. So if you notice, now we're going to, if we group together the first two now, we take that minus and group it with this and take the plus version, of the new thing and combine it with that, then in the first two, you have a g of x plus h. In the second two, you have an f of x. So we're going to factor those out. We're going to factor those out of their respective things. Okay? So all I did was factor out g of x plus h. And then here, factored out f of x. So if you look, what do you notice right here? This should look familiar. And then, same with this. This first thing that I put a circle around. What is that? The rate of change of f. And this over here? Rate of change of g. So that's why you do this initial step, and then you combine them, group them the way we group them, and then if you factor out, the rate of change of f and the rate of change of g separately emerge from this technique. So there they are. So we have g of x plus h times the rate of change of f plus f of x times the rate of change of g. Letting h get very small, we get this. So we get the one function times the rate. So this is the second. This is the second function times the rate of change of the first, plus the first function times the rate of change of the second. So the thing about the product rule is multiplication, you can switch the order, and addition, you can switch the order. So there's like 8 different ways or 4 different ways to write this. Okay? But if you switch the order here, it doesn't matter. If you switch the order here, it doesn't matter. If you switch the two terms, it doesn't matter, right? So this is in the order of the first function times the rate of the second plus the second function times the rate of the first. The first function times the rate of the second plus the second function times the rate of the first. Okay, and so here it is in the using primes. Here it is using our R notation, but it's all of them are the same. Okay, the rate of change of the product is the first times the rate of change of the second plus the second times the rate of change of the first. So it's kind of a hard one to mess up because the order you can change the order and you get the same thing. Addition, you can change the order. Multiplication, you can change the order. So you just take one of them and multiply it by the rate of change of the other. Then you switch it and you add them together. Okay? So let's practice. So here we have a function that is the product of 2. So the first thing we want to do is identify the two functions that we have that are multiplied together. So we got g and h. So we use these notations interchangeably. Sometimes a certain notation is the most helpful in a certain situation. Okay, so remember they all mean the rate of change of f with respect to x. All these notations. Okay? So it's just in certain contexts, writing certain things. One or some are more convenient than others. Okay? So we use them all. Okay, so what is the product rule? The plan is, again, we're going to take the first times the rate of the second plus the second times the rate of change of the first. So we need those rates of change first. So the rate of change of g is 8x cubed. What's the rate of change of h with respect to x? 6x. So now we just write it down. So we know our rate of change is going to be this right here. So we've got all the pieces, so we just write it down. Here's the first times the rate of change of the second, h, plus the second times the rate of change of the first. How could we check it? Right. So yeah, graph the difference quotient for f, graph this directly, and what should happen? Should be the same graph. Should be the same graph. So you'd have to, yeah, we did it. Okay, what about quotient? Okay. So let's first practice. Let's do it again. So practice writing out what would the rate of change of the quotient f divided by g of x be. What would that rate of change function be that we trust, that we know for sure it is? Write it down. Everyone do it. Okay, hopefully more of us got it this time. What will it be? F of x plus h? Okay, so it's our function at x plus h minus Did more of us get it this time? Hopefully more of us got it that time. Same thing again. The change in y over the change in x for a change in x of h. The change in y over the change in x. That's our constant rate of change, right? That's our constant rate of change formula. The change in y over the change in x. We know that when delta x gets very small, we'll get the rate of change at that x value. Okay, but actually this is not the way, so that was a good practice, but this isn't the way that we figure out what the quotient rule is. So instead, we start by changing the original function to a product. So now to derive the quotient rule, let's change that quotient into the product of f and g to the -1. So now I want you to practice applying the, now this applies both the product and the quotient rules, or sorry, chain rules, right? Because we've got a product here. Here's our first function. Here's our second function. But when it comes to taking the rate of change of the second function, what do we need? What kind of function is that? That's a composite function. So within the product rule, so this is kind of, in terms of the mastery exam, this is what it's all about. Within the product rule, we're going to have the rate of change of the second function. When we do that rate of change of the second function, we have to apply the chain rule to do that. So you are using the chain rule within the product rule. See if you can do it. Everyone see if you can write out what this will be. You're writing out the product rule. When you get to the rate of change of the second one, that piece will be using the chain rule. See if you can do it. Do you see it? See how this works? This is like the whole ball game with mastery exam. Learning how to use these rules in combination. So the structure of that thing is a product. So we're going to use the product rule. The first times the rate of change of the second plus the second times the rate of change of the first. But now when we get to this piece where we're doing the rate of change of the second, what does that require? We've got g of x plugged into something to the negative 1. So that's a composite function. So we need the rate of change of that, so we need the chain rule there. Does it make sense? So what is the rate of change of gx to the negative 1? It's going to be the rate of change of something to the negative 1, so it's going to be that whole thing with respect to g, then times the rate of change of g, which we did earlier as the chain rule. Okay, so here, this is written out here. So the first times the rate of change of the second, plus the second times the rate of change of the first. And what is, so this is applying the chain rule right here. This piece right here is, we look at the overall structure and we do the rate of change of that, which would be negative, but with respect to g, right? To the minus 2, then times the rate of change of g. So that was what we did earlier in class. That's application of the chain rule right there within the product rule. Anybody have a question? Do you see it? Okay, so we're not going to take the time to do the guts of the rest of it. So I'm just going to tell you from there what happens. So there's about 2 or 3 steps of algebra in between that take us to this final form. If you're interested, office hours, happy to work through that. But we get to this final form. And what is this? So this is the rate of change of the denominator, the denominator times the rate of change of the numerator minus numerator times the rate of the denominator over the denominator squared. This is our rate of change of a quotient function, a function of quotients. So this is using the R notation, this is using the prime notation. Okay, so to help you, like the seven dwarfs, right? So low, D high. Low meaning the denominator function, high meaning the numerator function. So low D high minus high D low. So D meaning the derivative over low squared. So we need some way to remember this because now, so listen, we've got subtraction in the numerator. The order matters. The order matters in the numerator now. You can't switch those because subtraction, you get something different if you switch, right? You get the opposite. So we've got to get the right one first and minus the next one correct. So this is not as foolproof as the product rules. But really, just if you know the pattern, all you need to memorize is that first little part. Low D high minus. If you can come up with that, then you can finish it. Low D high minus high D low over low squared. So if you just remember low D high, this is helpful to memorize it. No, we're just using it. We're just using it. It's just algebra. It's just some algebra. Trust me. Just trust me. Okay, I want to do an example. Okay? Ready to go on. Okay, so our example. So if we had sine divided by e to the x, that's what we're saying here for h of x. F of x is sine, the numerator, of the high, right, high, and then g of x, the denominator, e to the x, or low. We know it's low d high minus high d low over low squared. So we just need to get all those parts and construct this ratio, and that's our rate of change function for, what would it be, sine over e to the x. So all we need is what's the rate of change of f? Cosine. What's the rate of change of g? E to the x. So plug everything in. Low d high, the rate of change of sine, minus high d low over low squared. Anybody have a question? So I want to do just at least look at a harder example, one that's more like some of yours on your mastery exam. Okay, it's just so we'll really work on those on Monday, but I do want to look at a harder one. Can I go on to the next screen? Check the video if you didn't make it. So product rule, first times the derivative of the second plus second times the derivative of the first. Just write it down. So if you've got all those parts and you know what the product rule is, write down the rate of change function. Okay, so how about this? So this is, now we've got rules within rules. So when you have that, here's the key. The first thing you have to do is you have to say, what's the overall structure of the function? Or what's the big picture of this? That's going to dictate what the big picture rule that you choose. So is this, in its biggest sense, is it a composite function, is it a product, or is it a quotient? It's a quotient, its biggest sense. So we're going to apply the quotient rule, but then within the quotient rule, we may have these other rules when we're finding rates of change of those parts. For instance, we look at the rate of change of the numerator. What's that? That's a composite function. So within the quotient rule, when we get to the rate of change of the high, d high, we're going to have to apply the chain rule. Same thing with this is also a composite, so when we do d low, we're going to need the chain rule to do that. Okay, so first we'll write out what our high and our low is. So there's our high and our low. And we know our quotient rule. That's going to kind of dictate how we proceed because the big picture of this is a quotient. So what do we need? We need the rate of change of f and the rate of change of g. The rate of change of f is, this is the chain rule. Rate of change of g is also the chain rule. So this would be first. Actually, the order is different here. So normally we did this first. So it's the rate of change of e to that with respect to that times the rate of change of the interior function. Okay, so earlier in class we did some examples of those. Okay, so now we have low d high minus high d low over low squared is the rate of change of h with respect to x. This is the flavor of the mastery exam, these kinds of problems, knowing how to do this. So I'll just leave that up. If you want to come ask questions about that, feel free. Have a safe night tonight and weekend.